Good morning to all our participants in person and to all our online participants. As is the custom, we have a couple of announcements at the beginning before the speaker. The particular one for today is that next Friday there is FAME Lab, which is co-funded and co-organized by CoE-MaSS, NetTTP, and Genus, three different centers of excellence. And this focuses on, it's a competitive program where people present their research and it has to be presented in an accessible way to non-specialist audiences. And they're trained and they compete. And we wish them the best of luck for their competition in a week's time. Our speaker today, and we're very honored to have him in person, is Jacek Banasiak. Hopefully that's close enough to the correct pronunciation. He was born in Lodz in Poland in, do you want me to disclose your age or not? No, let's not.
A long time ago, you know.
A long time ago.
I remember dinosaurs, yes.
And he got his engineering MSc from Lodz and the his PhD from Strathclyde in Scotland, probably under Gary Roach. Then his habilitation at the University of Warsaw and the state title of professor in Poland. He worked initially at the Lodz University of Technology, where, according to this, you are still a research professor. Very nice. In 1992, he moved to the University of Natal as head of department. And since 2016, he has had a DST NRF Saatchi Chair in Mathematical Modeling and Methods in Biosciences, Bioengineering, and Bioengineering at the University of Pretoria. Jacek's research interests are integrated differential models in kinetic theory, asymptotic analysis of multi-scale problems, mathematical biology, and fragmentation coagulation theory. He has authored or co-authored 7 monographs and over 144 papers. He supervised 16 PhDs and was vice president of the South African Mathematical Society. He is editor-in-chief of Africa Mathematica and an associate editor of QM, and is a member of the editorial board of many other journals. He is a member of the South African Academy of Sciences and a fellow of the Academy, sorry, let me not botch that up. He's a member of the Academy of Sciences of South Africa and a fellow of the African Academy of Sciences, and is a fellow of the Royal Society of South Africa. And he has also, at some time in the past, about 10 years ago, received the South African Mathematical Society Award for Research Distinction. And around that time, the Cross of Merit, Silver in Poland for research. And the Polish Minister of Science Award for Science Achievements in 2022. A very illustrious career. And we hope you continue with it. It's not as though it's an end. And to that end, Jacek will be talking to us today about direct Lyapunov methods, known and less known.
Thanks. The problem is more or less the same story is when you, for example, prepare an RF application, then your CV actually is, incorrect. You spend most time actually updating your research. So, okay, thank you very much. Thanks for the invitation. Thanks for coming in person, whoever is here in person, and welcome to audience at large. My talk will be not really a research talk. It will be sort of like more historical talk. When I was preparing several courses, I spent some time reading newer and older books, and I picked up things which I never was taught at sort of like undergraduate classes. So I think that a number of aspects related to Lyapunov theory actually will be also interesting to you. So talking about Lyapunov method, actually you have to start with differential equations, and probably explain the history of differential equations. Okay, history of differential equations started with these two illustrious gentlemen. You may recognize on the left Newton and on the right Leibniz, who more or less at the same time developed differential calculus and also started working on differential equations. The problem was to a certain extent that Newton did a lot of stuff but didn't publish. And then actually, because of this, the very bitter rivalry started between them, and then sort of like respective courts of these two, in some sense, giants. And in some sense, you can imagine that Newton was at the beginning at a disadvantage, mostly because of notation. So this is actually typical notation of Newton for example, sixth order derivative, antiderivative. This is actually his writing of certain differential equations. You wouldn't recognize it. And this is simply x, f sub x plus y, f sub y is equal to f. So it's essentially first order PDE, but you wouldn't guess probably. So this is probably one of the reasons why Newton's work was not really as popular as Leibniz, who actually started with the notation we know about, and probably the first differential equation solved goes to Leibniz, who in 1675 wrote down the solution of this remarkable equation as he mentioned, and he actually wrote it in modern way using antiderivatives and so on. Newton's idea were slightly different. He essentially tried to present systematic way using infinite series, which were not well developed at those days. The theory actually was contained in a book, I call it book, written by him at 1671, Methodus Fluxionum et Seriem Infinitarum, translated later into English and published eventually only in 1736. But actually, you can find it online with English, old English translation, and you can see how awkward the notation actually was, how difficult to understand what he had in mind. Okay, so the bitter rivalry actually had two very bad effects in some sense. In my opinion, it stifled development of differential equations, mathematics in general in England, in the UK, because you couldn't compete with it. We had the same story like in Poland when collaborator of Einstein, Infeld, came to Poland after the war, and it was so big that nothing but general relativity was worthwhile to study. So in some sense, this happened to Newton and British mathematics. On the other hand, actually, because of the strength of British Empire in those days, actually the ideas of Leibniz were pushed back and also largely forgotten. Anyway, okay. So just we'll be talking mostly about systems, finite dimensional systems, or mostly autonomous differential equations. So this is our basic object of interest. So about the right-hand side, we assume, of course, that it's sufficiently regular, defined somewhere, and so on. I will not go into technical details, but this is the animal we'll be looking at. And going back to the times of Newton and Leibniz, and later, more or less up to late 19th century, people were studying differential equations by solving them. Simply, and unfortunately, it continues in many centers in the world. Actually, if you think about differential equations, start thinking how to solve it, how to write down the solution. Within this context, In the 19th century, models of the universe of solar systems were very popular. Actually, the interest in this problem has been, I think, revived to a certain extent by Netflix series. It's not really related completely to this story, but essentially it's three-body problem. So this is a system of Newton's equations describing interaction between three interacting objects of different masses. And as I said, we see in this context in those interests actually whether systems like that are stable or whether they will collapse sooner or later. And in this context, Oscar II, King of Sweden, established a prize for anyone who finds a solution to this problem. So it was formulated as follows: given a system of arbitrarily many mass points that attract each other according to Newton's law, under the assumption that no two points ever collide, trying to find the representation of the coordinates of each point as a series in a variable that is some known function of time, and for all of whose values the series converges uniformly. So it was formulated not by the king himself. I think it was Mita Kleffler who formulated precisely the topic, but still actually it was interesting intellectual environment. Can you imagine, for example, I don't know, President Trump asking the question, about the stability of the universe, or for that matter, actually, President Zuma. Yeah, I was going to go. So this was the problem, and you can see that it's still written in the context of thinking about differential equations as something which requires just writing down the solution. But it was a breakthrough. But there are no custom solutions to the system. However, in 1912, the Finnish mathematician proved that there exists an analytic solution to the three-body problem in the form of a power series in T to the cubic root of T, which converges for all real T except for initial conditions corresponding to zero angular momentum. This is significant, essentially. It was later generalized to n-body problem and so on.
But it was, did he actually state the solution?
Well, this guy, yes. I mean, he wrote the series and then proved that it is converging. But as in many cases with finding explicit solutions, this solution is more or less useless because in the 30s, Berezovsky calculated that if this series to be used for astronomical observation, it will take at least 10 to, I don't know, my imagination don't go that far in zeros, so it would take that amount of terms to make this series useful. And then unfortunately starting from this, as in many cases, unfortunately in mathematics, it actually was a fountain of new results. So especially in China, people were starting finding, new periodic orbits, new solutions, and something like that. Additional 1,200 solutions and so on. The problem is, unless one can prove the stability of such solutions with respect to small perturbations, such solutions are useless, both for physics, because we never have actually exact information about the process, and also numerically they can be tested. Because you don't know what to do with them. And unfortunately, a lot of research in applied mathematics is going in this direction. You produce something which you really don't know how it's related to real life. And really with this realization, foresight in some sense, King Oscar II prize went to Lyapunov, who didn't solve the solution, but he realized the new method of attacking problems. And he realized that to understand ordinary differential equations, one has to abandon the study of their individual solutions in favor of considering them as a whole and studying their mutual dependence. In particular, the aim of Poincaré was to see how the existence of solutions of particular type, stationary solutions, will influence the qualitative structure of the set of solutions of the equations. And in notation by Weierstrass, the guy actually Weierstrass wrote that this work cannot indeed be considered as furnishing the complete solution to the problem proposed, but it is nevertheless of such importance that its publication inaugurate a new era of celestial mechanics, and indeed.
We were just discussing whether that was in fact how long Poincaré lived. We just confirmed that they're having the date.
How do you think that it was
That 84 should be
1884, 1912?
1854.
1854. Okay.
That makes him very young. I mean, he died at a very young age.
Yeah. Maybe I have to double check. Okay. Yeah. Sorry for this. It's strange because actually I did the captain. It's not simply gone. Yeah. Yeah, you are right. Anyway.
Sorry for that.
No, that's fine. It's good actually. It's, I will, if I still remember, which is not in my age, you know, correct this, so I will not make this mistake next time.
If you make that kind of mistake with my age, I don't mind.
Okay, so essentially, the crucial role in Poincaré thinking was the concept of the stability of solutions of differential equations, both in time, that is how the solutions of this system behave as time goes to infinity, and also structural stability, so how the solutions change when the equation itself is slightly deformed. So in this case, I wrote, you know, additive deformation, but any deformation can be essentially written in this way, where here is the difference between the original and the new right-hand side. So these two types of stability actually shaped the life of people working in differential equations since then to large extent. Okay. Okay. So as I said earlier, we start with time stability, so the behavior of solutions as time goes to infinity. So we are looking at the system of equations. We assume that the solutions are globally defined, and many theoretical questions can be reduced to studying the stability of the equilibria, so the solutions of constant solutions of this system of equations. And usually you can actually shift everything to zero. Okay, and then we have different concepts of stability, which we'll be talking about. Stability itself is just the fact that if you start sufficiently close to the equilibrium, then you stay all the time close to equilibrium, so you can, for example, move around. Okay, but you don't actually escape from this. Asymptotic stability is actually where you collapse on the equilibrium, so we eventually go to the equilibrium, and then global asymptotic stability is that essentially you have only one equilibrium, everything else in the domain of interest actually converges to this stability. It's something like holy grail of stability analysis. Okay, essentially looking at stability requires some historical trip back, also in some sense to Newton's time. So essentially, differential equations came about as description of mechanical motion in the universe, and people always were interested in the relation between, for example, energy of the system and how it moves. So, and essentially most of physics relies on the hypothesis that physical systems are lazy, so they behave so as to minimize some sort of energy. Okay, and essentially it goes essentially to Newton's time. So starts with Bernoulli's, L'Hopital, and so on. And then these ideas were converted into proper theoretical statements about variational principles of mechanics, like Fermat-Petit, Euler, Hamilton, and so on. Okay, roughly speaking, there are two main. Okay, two main. I'm not going into details here, so if you are specialists in this, forgive me. Essentially, it turns out that any equation of motion realizes some stationary point of some functional related to energy. And in particular cases, for example, when motion is such that along the motion actually energy doesn't change, then as long as you are at the minimum of the given defined energy, then this trajectory must be stable. You cannot actually suddenly jump from the minimum level to start moving new. And actually this in 19th, especially starting from the 19th century, this essentially, I would say that this generated the development of functional analysis, because the problem was that equations of motions are formulated as derivatives. This requires continuous differentiable functions. On the other hand, the energy integral is integral. And there is a mismatch between integrals and continuity. Okay? And because of this, for example, practically the variational calculus is not really complete without going into L2. Or because essentially you need some sort of like completeness of the underlying space here. And you cannot do this. So with respect to the integral, let us say norm, the space of continuous function is not complete, and you cannot actually minimize in this space. So actually this actually prompted, these ideas prompted actually the development of most of 20th century mathematics. But this is actually a side thing. So we are back to stability with respect to time, long time behavior of systems. And as I said earlier, for a long time, people were under impression that essentially any stable point must correspond to minimum of certain energy. And for example, if you look at, let us say, Hamiltonian formulation of motion, so you have a system of two equations. H is the energy. Hamiltonian is in most cases the total energy of the system. And any motion obeying this system of equations satisfies the conservation law, which is here. And it led to something which is called Lagrange-Dirichlet. So if we have stationary point of the system, and if the energy has isolated minimum at 0, 0, then this point is stable. Unfortunately or fortunately, the converse is false. So they are stable equilibria, which are not realizing minimum of energy. It's interesting actually when we get back to Lyapunov functions, and if you start talking about general Lyapunov functions, the converse is true. Okay, and this was given by, I think originally it was given by Pine-Lever. So this is actually the Hamiltonian system. It's Hamiltonian given a very nice Hamiltonian C infinity, but it can be proved that it has a stable equilibrium at 0, but it's not a minimum of the Hamiltonian. So, but remember that here we are in the mindset that everything must be related to physical quantity, physical energy. And here enters Lyapunov. He said, forget about this. You don't need to have anything physical to get the same results. It is sufficient to create an axiomatic theory. So it is enough to have a function which is, no surprise, called the Lyapunov function, which is essentially a differentiable function defined somewhere, which is strictly positive everywhere apart from the suspected equilibrium, so apart from zero in our case, and such that this product, dot product, so you take the gradient of V times the field, that this is smaller or equal to infinity. No mention of energy, nothing. It's I mean, if you have energy, energy typically is Lyapunov function, like in the Hamiltonian case, but not every Lyapunov function must have an interpretation of energy. Okay, and the idea of the proof, I mean, the proof is not trivial. I still don't understand fully the proof, but it's short. But the idea essentially is that this object, what is important. This object doesn't, to calculate that something is Lyapunov function, you don't need to know the solution of the differential equation. This is defined by the equation, not by the solution. But actually, this fact shows that the trajectory, the Lyapunov function along the trajectory must be, well, non-increasing here, generally decreasing. Okay? And because of this, roughly speaking, you can prove that whatever, if you start close enough to the equilibrium, I mean, because of the, roughly speaking, the shape of the Lyapunov function, you cannot escape. So this is actually the crucial point, the fact that the Lyapunov function is decreasing. Okay, and one more thing which is very important later, which becomes very important later, is in particular the sub-level sets of Lyapunov functions are invariant. This is very important information because it gives you domains of attraction, invariant sets, everything which is important in the applications. Okay, so I mean, I will skip this part, technical part. What is actually just I mean, there are not really, don't have really students here, but again, what is important is that very often Lyapunov function is used, the Lyapunov theorem is used in the wrong way, not completely correct way, I would say. Because very often you have equilibria which are not inside the domain of the definition of the dynamical system. You have equilibria, for example, at the boundary, but then actually you can twist the proof. Essentially, the proof of the original Lyapunov function more or less tells you that if this is the level curve of the Lyapunov function, then you cannot cross it because of the monotonicity of the Lyapunov function, and you cannot cross this part because this is actually the boundary of the some invariant set. So essentially, you combine these two results, and then the results are kosher. Now, if we slightly strengthen the result, the inequality here, so we make it strict inequality, then you not only have the fact that trajectory will not escape from the equilibrium, but actually it will collapse on the equilibrium. Okay, I will skip the technicalities, proofs, and so on. Okay. And then there's another story which is appears in applications, question of global asymptotic stability. So I have rejected many papers in mathematical epidemiology that people claimed that if you have, for example, a single equilibrium, for example, in RD, and you have strict Lyapunov function, then sometimes people prove that there is no periodic orbits inside, and then this equilibrium must be globally stable. It's not true. Okay, so it's not sufficient to have single equilibrium and strict Lyapunov function to claim that you have global stability of the equilibrium. Well, you have to spend some time to cook up an example, but this is one of the examples which I found. It's a nice system, nice Lyapunov function, and it turns out that I mean, it's only sorry. It's only one equilibrium at 0, of course. And these are trajectories of the system. And you can see that something already is happening looking at the arrows. So clearly, when you are relatively close to 0, 0, everything actually is nicely converging here. But here you can see that the arrows actually start flowing out. And the reason for this is that Lyapunov, the level sets, or sub-level sets of Lyapunov functions are like that. They are nicely closed up to some point and then start to open up. So essentially what you have here, you have a throw like that. And so you can have a trajectory which starts, let us say here, and goes down the level sets of Lyapunov function, but actually moving away from 0. Right? So this is actually an example that you have a single equilibrium, you have strict Lyapunov function, everything is fine, but there is no global stability. Okay, and then there is a point which actually clinches the story of global stability. You must ensure that your Lyapunov function actually uniformly blows up if you go to infinity. So they're bigger, bigger, and bigger. And essentially, then it makes that, you know, whenever you start your point, then you will find this set omega c, this invariant set of the Lyapunov function, which encloses the starting point. So you must stay in a bounded domain. And then if you are in bounded domain, then everything actually by compactness must go. Lyapunov, this is essentially the more or less known stuff. But Lyapunov function has a lot of other applications. First of all, you can, if you know Lyapunov function, you can estimate the rates of convergence to equilibrium. And this is very important because, I mean, quite often now important people ask, okay, so you prove exponential stability. So it means that as time goes to infinity, then the solution converges to equilibrium. Well, we don't have infinite time, you know. But then if you know that the convergence is exponentially fast, e to the power minus t, so if the error is e to the power minus t, then already after 2 or 3 units of time, you are practically at the equilibrium. So knowing how fast actually the solutions converge to equilibrium is also important for practical purposes, that you don't have to wait infinite time to get your information. And then, so in sort of like more advanced books on dynamical systems, you have different types of stability. I will concentrate only on exponential stability, which is the one which you get if you linearize, essentially. If you have linear stability, then you have exponential rates. So everything converges to 0, equivalent 0 at some sort of like exponential rate. And then you can prove that if essentially, if you can construct Lyapunov function which has sort of like power-like behavior, that this translates into exponential behavior of solutions. Okay, so this is one application. And then the other, I will start with an example, because now we are moving to structural stability. So what happens when you change the right-hand side of the equation? And a simple example here is, for example, you have a classical epidemiological system, so-called SIR system. I don't know whether I have to explain. So essentially what happens is that you have infections here, you have some sort of like birth, death, and I introduce immigration. Okay, so now suddenly, I mean, it's a typical example, you know, we remember from COVID, the problem was immigration. Yes, because starting from China, everywhere else actually started immigration. So the question is, can I say something about stability of this system with immigration if I know something about the system without immigration? So this is perturbation of the original system. we have here single so-called disease-free equilibrium. So something that there is no disease. So it's essentially a population equilibrium point. And one can, okay, remove everything to zero to make life a little bit easier. And it turns out that you can construct the Lyapunov function for this. This is V, and everything is now. So I can prove that this equilibrium is globally stable and so on. So now, how I can use this fact to the system with immigration? So with this term here. Well, I can try to stretch my Lyapunov function so that actually it will cover. So I simply take the same Lyapunov function and will plug in this Lyapunov function into the new. Okay. And important thing to remember, level curves of Lyapunov functions are invariant sets. So if the solution is here, then nothing will go in this direction, everything must stay inside. So that's why I wrote this. So let me try to do the same Lyapunov function, for the system with migration. And it turns out that the derivative, sorry, this actually should be dot, the derivative will be still negative as long as, I mean, certain inequalities are satisfied. So essentially, as long as the number of infectives will stay outside curves like that. So the situation is like that I have a solution. This solution will go exponentially according to the Lyapunov function to the moment at which actually it crosses this level line. And now, if I can prove that at this point, this solution is inside one of the sub-level sets of the original Lyapunov function, then I know that the solution will stay there. And using this actually without, I mean, again, without going into technicalities, I can prove that with immigration, my number of infectives, which is something which I need, can be controlled by the rate of immigration. So I have sort of like explicit formula to control. So this is essentially the idea, and this idea can be turned into proper theory, which is quite often considered to be, I mean, it's called inverse Lyapunov function theory. So essentially, first of all, you can prove that if you have, for example, exponentially stable equilibrium, then I have Lyapunov function. So you can see, I told you, talking about Lagrange-Dirichlet principle, that it's not true that energy always must take at a minimum at equilibrium. Lyapunov function must. So if I have stable equilibrium, exponentially stable equilibrium, in this case, then I have a Lyapunov function which satisfies these conditions. So I don't have to rely on the prior knowledge. As in the example, I know that such a function exists. Okay. I mean, the construction, I mean, it's relatively simple, but it requires, I mean, calculations are unpleasant. But something like that happens. And then essentially, again, I will just quickly go through these slides. In abstract setting, I consider a perturbation of my original system. I assume, I make some assumptions about the perturbation. So there is actually vanishing part. If you have vanishing part, then the equilibrium stays the same. If you have non-vanishing part, then you may lose an equilibrium, for example. So I have these two parts, and then I have the result. Okay, and I mean, calculations are the same essentially as in the example. So essentially, I will prove that my solution will exponentially converge up to the moment when it meets certain isocline of the derivative of the Lyapunov function, and then I can prove that actually this point is inside some sub-level set of the Lyapunov function itself. So this is something like that. And then my final part of the talk is about non-differentiable Lyapunov functions. So going back to the proof of the Lyapunov function. So if you do any proof, you try to build, extend, for example, results. You go through any proof and you should actually sort out what is the essence in the proof of is a tool. And if you look at the proof of the classical Lyapunov theorem, it turns out that the fact that the Lyapunov function is supposed to be a differentiable function is just a tool. It's a tool to ensure that the Lyapunov function is decreasing along trajectories. So the whole proof, the whole theorem can be reformulated that if I have a function v which is positive apart from the equilibrium, and if it decreases along trajectories, then everything works. So now let us try to find other tools to check whether a given function is decreasing or not. So again, some advert for functional analysis. Again, for a long time, people deeply believe that practically all functions are continuous, they're differentiable, and so on. I think throughout 19th century, still I think there was a belief that everything is sort of like smooth. But Weierstrass constructed this particular function, sort of like fractal type of function, and it is the function which is continuous, and there's no point at which it's differential. Okay, well, you can say, okay, Weierstrass is a strange person, you know, but we still live in where everything is smooth. But unfortunately, later came Banach, who proved that essentially, if you walk and you pick up a arbitrary function, that it strangely that it doesn't happen yet somehow, but in general, in the whole universe of functions, most functions, practically all functions are continuous. All continuous functions are not differential. Okay. So people start thinking, because differentiability is important. You know, you work with differential equations, differential functions, differential functions. So unfortunately, as with generalizations of most definitions, you can generalize the definition in very different ways, depending on what you want. So there are so-called distributional generalized derivatives, which are very useful in linear PDEs. But they have also many problems. For example, the product rule doesn't hold typically for distributional derivative. They cannot be used in optimization problem. If you are looking for a maximum of a function which is not differentiable, and to calculate this distributional derivative, that at extremum distributional derivative doesn't have to be zero, okay? Because it's defined almost everywhere. Okay? So now, if you want to do optimizations, then you go for subdifferentials, which is essentially, I mean, it's all possible tangent directions. So if you have absolute value functions, then subdifferential will be all, so with multi-valued function which consists on all directions, essentially tangent to the corner. They can be used to optimization, but of course, dealing with multi-valued function has a lot of problems. And then in real analysis, when you are looking for, if you want actually to get a tool to observe monotonicity, then you go rather to real analysis and look for generalizations in this field. And probably the most general version of them is Dini derivatives. Unfortunately, there are 4 of them. If you remember your calculus, probably 2 or something like that. Good thing about definition is that they always exist. So upper and lower limits always exist. But the problem is that they don't have any properties of normal limit. For example, they are not additive. There are problems. So again, applicability is limited, but this is probably the most general context which can allow you to use derivative to determine whether a function is monotonic. Okay. A good thing actually is that if you know that your function is somehow differentiable, so if it has, for example, one-sided derivatives, then one-sided derivatives are Dini derivatives, and so on. Lipschitz continuous function has Dini derivatives, so it's almost everywhere differentiable. So if you know something more, then actually you can fit into the theory provided by Dini derivatives. Okay. So in particular, if you have for any Dini derivative, your derivative of Dini derivative of function is a constant sign that this is monotonic function. Okay. And then this can be used simply to non-differentiable Lyapunov functions. So the whole, I mean, the first Lyapunov, so stability, holds for as long as you have any Dini derivative of the Lyapunov function constant sign. Okay. The problem is that, of course, with Dini derivatives, you have a problem with differentiation of compositions. So mostly what we are working with are sort of like absolute values norms, which are Lipschitz convex, so they are differentiable almost everywhere. So then actually you have more or less the same formula as for differentiable function. And just to conclude with an application, I mean, 2 applications quickly. So for example, if you can write your right-hand side in the following form, this is typical form for epidemiological problems. And Metzler matrix is a matrix which is positive of diagonal. Okay, so along the diagonal you can have anything you want. And then if I have a positive vector C such that multiplication of this C times this vector max is strictly smaller than 0 for any x in omega, then 0 is globally asymptotically stable in the invariant set. And this actually uses the Lyapunov function, which is not differentiable. So we have absolute values here, and this is, for example, the formula for the derivative which you use here. And the last example, which I would like to see, I mean, compartmental systems. So compartmental systems are systems of equations such that the Jacobi matrix of the right-hand side is a Metzler matrix. So roughly speaking, there are systems in which nothing is produced, so everything must be balanced. And there is only sort of like influx, positive influx. Okay. So for example, if you take a linear system like that, this is compartmental if and only if all diagonal terms are non-negative and sums in columns are non-positive. And then there is a beautiful result which tells you that if I have a compartmental system, then essentially the sum of the right-hand sides taken with absolute value is monotonely increasing, so it's a Lyapunov function essentially, slightly less than Lyapunov function. And then every orbit is either unbounded or it is bounded that it must converge to an equilibrium. So in systems like that, you don't have periodic orbits, nothing like that. Everything must converge to an equilibrium. It doesn't have to be a unit equilibrium, but it always converges to an equilibrium. And just to, the proof is very unpleasant, long time unpleasant, but then actually just brighten your Friday at the end. I will show you pictures. So there is a very simplified system of so-called gonotropic cycle of malaria. So essentially, it doesn't matter really what is the meaning of this, but this is a part of the full system. And so roughly speaking, there are breeding mosquitoes, questing mosquitoes, and returning mosquitoes. So essentially, they go back to, they are unsuccessful in breeding, they can return to the breeding site. And this system is compartmental under certain assumptions here. And what is interesting here is that under certain conditions, so if delta is equal to beta, it has a continuum of equilibria. And people who work with dynamical systems know that the continuum of equilibria is first level. Because you practically know, I mean, there's no linearization of variable, nothing like that. You cannot say that if you have a continuum of equilibria, then an equilibrium is, for example, stable, because you have a continuum. So you pick up an equilibrium, and in neighborhoods, you have in any neighborhood you have other equilibria. So nothing can actually move there. So you don't have asymptotic stability of some of any sort. Okay, and in this case, what happens is, I mean, if you think that this is a simple problem, this actually it's not a very simple problem. Here you have trajectories, and actually, if you slice them, then actually you will find that you have a continuum of stable invariant subspaces, and in each subspace like that, everything goes to this equilibrium, but one of the equilibrium on the line. So you have essentially a continuum of slices of stable invariant manifolds with single globally attracting equilibrium on this subspace. And with this, I will finish. Thank you very much. More or less I kept in time.
Thank you very much for a very interesting talk, both historic and modern. Sorry.
Okay, you're too tall.
Are there questions from our audience in the room?
Historical question. So, which came first, the Hamiltonian formulation or the Lagrange formulation?
Lagrange is mid 18th century, Hamilton is early 90s. It's not much later. And I mean, they're very close related. Hamiltonian and Lagrange are conjugate functions. Because Hamiltonian is PQ minus or something converse, I don't remember. But essentially, they're almost, I mean, in classical mechanics, they are almost the same. Lagrangian is the difference of energies, Hamiltonian is the total energy. But I mean, the benefit of Hamiltonian is that it leads to the system, and then actually space analysis of Lagrangian leads to second order equation, which is a little bit more complicated.
No, the Lagrangian.
Second order equation, yeah.
So how much smoothness do you really need? Continuity is not enough.
For what?
To set this up. So you needed, you said firstly that continuity is not enough because you need differentiability of some form.
For Lyapunov function?
Yes, to get your equilibrium to work and all of that.
Well, no, I mean, okay, so starting from the system of differential equations, then all this theory requires at least Lipschitz. Because it requires uniqueness. If you don't have uniqueness, you cannot do much. Then I mean, if you have Lyapunov function, then in some sense I can say I don't need don't need even continuity as long as I have a tool. Yeah, I mean, sorry, no, I need continuity. No, but I need continuity. I need continuity of V. Because I sort of like I use minimum. I mean, Weierstrass principle.
So V has to be continuous. And probably almost everywhere differentiable.
Not necessarily. I mean, as long as you can calculate the derivative.
Because lots of your proofs actually use the derivative.
Yeah, but
the grad of the.
Yes, but
hidden in there.
Yeah, it's hidden, but then I mean, in both. Okay, so the first part require differentiability. Yes, because I differentiate. In the second part, I said, okay, as long as I can prove that my function V is decreasing along trajectories, I don't need anything more apart from continuity. And for example, the proof for the last theorem about compartmental systems doesn't use the concept of Dini derivative. They simply, because the proof is given by people working in control theory.
Okay.
It's Mekta, some Japanese guys. And then they very laboriously split, because they're absolute values. So they split the set of indices so that actually everything nicely can be nicely calculated. But this is actually simply the fact that here you are given a function. So F is Lipschitz at least, and then you have absolute value. Okay. So yeah.
Very
So,
interesting.
okay.
Thank you. Are there questions online? Are there any questions?
I killed everybody.
Then any further questions? Any questions about the damages that were done to English mathematics by hanging on to Newton and their obsession with series? That was the next one. They didn't believe in going into working with abstract quantities like norms and that type of structure.
Someone has a hand online.
Okay.
Okay.
Sudan, you can speak.
Thank you. Yes.
Oh, Sudan, hi.
Hi, that was a wonderful talk. Thanks. I was teaching this topic, so I was glad to hear some of the finer points. I was wondering, I think the ingenuity in using the Lyapunov method is to find the Lyapunov function, to use some creativity to actually find one that works. I mean, normally the ones that we teach are straightforward, sum of squares and so on. I was quite intrigued with your example of the disease model, and the function that you put forward there had a S and a ln S. It was not algebraic. It reminded me of a solution actually for I in terms of S. How did you come up with that Lyapunov function?
Oh, well, it's not me. I mean, there are certain standard tricks in Lyapunov functions, and then you have a lot of people working on them, and then getting Lyapunov functions are I mean, I know a person who actually set up a price of, I think, 1,000 euros to find the Lyapunov function for some system of infinite dimensions. But roughly speaking, for this case, I can tell you more or less that this goes back to Lotka-Volterra, because I mean, all these systems are Lotka-Volterra type in some sense. Because I mean, disease system is Lotka-Volterra, it's predator-prey. You have a predator who is infective and prey which is suspected. And then logarithmic functions, if you teach this course, logarithmic functions appear as the first integrals of Lotka-Volterra. So what you do, and actually, I mean, in one of the talks of this type, which I gave, I give an example. So you essentially start with, so you have Lotka-Volterra, you know that you have first integral involving logarithms, and then you simply, again, you stretch. So you make some constants, movable, and then you plug this Lotka-Volterra Lyapunov function to your new system, and you try to balance. So this is how models like that are constructed. And then in some sense, to answer your first point, and talking about inverse Lyapunov functions, I am very often accosted by people who actually believe that Lyapunov function is only to prove the existence, to stability of the equilibrium. This is not a tool which can help you for particular application to prove the stability of an equilibrium. This is a tool to prove other theorems. So I can, for example, here, if you know that there is Lyapunov function, I can prove the theorem about structural stability of dynamical systems. If you go, for example, to something which is called center manifold theory, then the fact that stability, asymptotic stability at the center manifold actually extends to the full system, is done also can be done by inverse Lyapunov function theory. So inverse is a theoretical tool which allows you to prove other theorems, not to prove that particular equilibrium is stable. So you have to understand that it's a different purpose for constructing this.
Thank you.
Okay.
Thank you. Any other questions online, in person?
Yes, hello.
Hello.
Yes, hi. Thank you, Prof. That's a nice talk. If I may follow up just about the Lyapunov functions and the energy method. It's easy to construct the Lyapunov functions. Just I want to, is there any way of uniform of constructing the Lyapunov functions for different type of systems?
As I said earlier, no.
Yeah.
It's just a game. I mean, people sometimes spend months, years actually trying to get Lyapunov functions. As I said, you know, there are some hints. As I said earlier, you look at a similar system, for example, or simplified system, and you try to use the Lyapunov function and slightly modify it, and then play in the same way as I played with this SIR model. So I used the Lyapunov function for a simpler model and proved that it can be used somehow to determine, for example, if for example, instead of constant I had, for example, some function of I which would vanish at 0. So essentially I would have the same equilibrium, then I could use the same Lyapunov function under certain conditions to prove that this perturbed system also has the same equilibrium and the same type of stability. But there is no general way. I mean, people are writing papers. If you try, you know, listen, I mean, Russian British Korobelnikov, who actually became famous, produced several papers because he realized that, for example, you can use some tricks whenever F to the right-hand side has some convexity properties, and then was able actually to apply this to a class of epidemiological models. But in general, I mean, there is no rule.
Well, thank you very much for your talk and answering all the questions, and the interesting view on history and the modern stuff. And we thank our participants and the online participants.
Thank you very much. We don't believe that Newton's